Hi, in this video, we'll try to see how we can use ADC or analog to digital converter on Raspberry Pi Pico boards. This video is applicable to Raspberry Pi Pico as well as Pico W boards. However, in our course, the primary focus is on Pico W boards because we want to understand how to create embedded systems as well as we are going to see how we can connect it to internet and how to perform IoT experiments. This video is about understanding the usage of analog to digital converter which is present on RP2040 microcontroller. This microcontroller is the heart of Raspberry Pi Pico boards. So let's get started. Now before we understand or before we look into how to use ADC on the Pico board, it's important for us to understand what exactly is ADC. Now, if you know what exactly is an ADC and how it functions and what it's used, you can skip a few minutes from this moment and onwards. But if you don't, I would suggest please stay and please understand. ADC or analog to digital converter is particularly a circuit. It's a peculiar circuit which is used whenever we want to measure the applied voltage. I repeat, when we want to understand the applied voltage connected to any pin of microcontroller, we want to use ADC. Now, why is that? Because many a times whenever you connect or whenever you give any kind of voltage to a microcontroller pin, it will be categorized either as logic 0 or logic 1. But there are cases where we don't want that. And what we want is to know the exact voltage. For example, if you are For example, when you want to know the voltage of a battery, then you need to understand exactly the voltage of the applied signal. You can't just say that the battery voltage is 0 or 1. So this is one case. Apart from that, there are many sensors as well which give the output voltage in proportion to the applied or in proportion to the physical quantity that they are sensing, like temperature or let's say LPG detector, and many such examples are there. Now, another thing to understand is when we say analog signals, then what comes in our mind is a sinusoidal wave. Here, that's not the case. Analog signal is referred to as any signal whose voltage is unknown and we want to know that. It can be a sine wave, it can be a triangular wave, it can be a plain DC voltage. Another constraint is most of the times your voltage needs to be between 0 to a top voltage or the maximum logic voltage that your microcontroller supports. For older microcontrollers like 8051, PIC series, APR series, the maximum voltage was 5 volts. Nowadays, including Raspberry Pi Pico, it's always 3.3 volts. So you can convert 0 to 3.3 volt voltage into its respective digital value using ADC. And then you can use that digital value or number to find out what was the exact applied voltage. Now, this image will give you a very simple understanding or visualization of how ADC functions. This is a very simple 3-bit ADC and the voltages shown are between 0 to 5 volt. As you can see, the job of ADC is to split the minimum and maximum voltage value into equal number of steps. How many steps here? We have 8 steps. Why we have 8 steps? Because it's a 3-bit ADC. So a 3-bit ADC will convert the voltage into or will convert the entire measuring range into 8 particular steps. The number is very usual because when you have 3-bit digit from 00 to 111, it gives you a value 8 or basically 2 raised to 3 will give you 8. Now if you have a 8-bit ADC, then the maximum number of results you have is 256. If you have a 10-bit ADC, then you have 1024 results. If you have 12-bit ADC, you have 4096 total number of results. The higher the resolution, the better differentiate you can do between the applied voltage levels. And essentially, what is happening is whenever your voltage is between any two levels, it's just given with the number of that particular lower level. So this blue line currently is here from this voltage to this voltage. So it will be completely truncated and it will be given with a value 0, 1, 1 and so on. Now how this happens and what are the concepts behind it? The concepts are actually very simple. We have resolution as spoken. So you have 8-bit resolution, 10-bit resolution and 12-bit resolution, which are most popular ones on microcontroller. Based on the resolution, you can find out the step size, which is equal to Vref divided by resolution. Now Vref here means this 5 volt or the maximum voltage that your ADC can convert into the digital format. Many microcontrollers also have an adjustable Vref, with which you can reduce the maximum voltage and have a further fine or small step size. This gives you the step size. Next is digital out. So what is the digital out that is going to be generated? This is more of a understanding formula, but you don't use it. The digital out that a microcontroller will give will be the analog applied input voltage divided by your step size. This is what microcontroller is going to give us. And what was analog in? We will be calculating this using this digital out, multiplying it by step size. As simple as that. You will understand these concepts in finer details as you go on and keep experimenting with ADC. Now, digital out is what any programming or any microcontroller coding is going to give us. Our job is to find out the step size, multiply it with that digital out, and here you go, you get your applied analog input voltage. Now, what are the modules? What is available on Pico W board? Let's see that in a detail. So Pico or Pico W, basically these boards are built upon the microcontroller RP2040, and RP2040 has a 5-channel 12-bit ADC. It means it can convert the 0 to 3.3 volt voltage level or entire voltage range into 4096 total number of results, starting from 0 to 4095. Now, out of these 5 channels which are available within RP2040, one channel is dedicated to the internal temperature sensor. Yes, there is an internal temperature sensor on RP2040 and one of the channel is already dedicated to it. So, what we remain with is 4 channels of 12-bit ADC on RP2040. Now, I am giving stress on RP2040 because it's there on RP2040, but on the Pico boards, we have given with only 3 channels. Okay, those 4 channels available on RP2040 are pin number 26 to 29, but on Pico W or Pico boards, you have only pin number 26 to 28. Total 3 channels that you can use for analog to digital conversion. This 12-bit ADC, as said, gives you a value between 0 to 4095 because it's a 12-bit ADC. Now, this is particularly confusing and it may confuse you a lot. But in order to keep the standard of MicroPython as it is, what is done in the MicroPython SDK for Raspberry Pi Pico, the ADC analog output value is scaled to 0 to 65,535. It means to 16-bit. So, in all our calculations, we have to assume that our ADC is 16-bit ADC. Actually, it is 12-bit. But the library is going to give us value between 0 to 65535. So, all the calculations, every formula that you apply should be focused to this resolution only. Now, if you look at the pins, as said, GPIO 0, GPIO 1, GPIO 2. These are the pins we have available. Sorry, channel 0, channel 1, channel 2. That is GP 26, 27 and 28. These are the pins available for using ADC or ADC inputs. ADC 0, ADC 1 and ADC 2. GPIO 3 is not available on Pico W board and GPIO 4 or channel 4 is given to internal temperature sensor. So these are the three channels available with us, and we can experiment with these three channels as we want. Now, what is the simplest experiment that you can do with ADC? It's always connecting a potentiometer, trying to give a varying voltage between 0 to 3.3 volt to the pico board and see if it gives the intended output or not. Let's do that experiment, or let's do that exercise now. But before doing that exercise, we also need to see what are the MicroPython syntaxes, or what are the MicroPython lines or function calls that we need in order to use ADC. Now, ADC on RP2040 by default will use 3.3 volt as reference voltage. You don't have to do any changes for that. All you need to do is you need to initialize ADC like this. So ADC is equal to machine.adc. Needless to mention that you need to import machine. And here you simply give the ADC channel number 0, 1, 2, 3, 4. As said, 3 and 4 are given to 3 is not available and 4 is given to internal temperature sensor. So if you want to use the temperature sensor, you give channel number 4 here. Otherwise, you give anything between channel number 0, 1 and 2. This is initialization of the ADC module in MicroPython. Then all you do for reading the value is simply initiate a variable equal to adc.read underscore u16. That will read the value from declared channel and give it to you. Now, for the sake of very simple experimentation, as I said, I am going to connect a pot between VCC and ground and give the variable point to GP26. Okay, it's a mistake here. It should be GP26. I just connected it to pin number 26. It should have been here. I will rectify that in the actual presentation that I give you. For now, just understand this. Okay. Now, let's try to write down the code for it. Okay. I'll just keep this for now. I'm going to copy this code and then we'll try to understand every line one by one. Now, as I told you, there is an important concept called resolution of ADC. Here the resolution is 65,536 because 0 to 65535 total number of results is 65536. So because of this resolution, you can calculate the step size. What it would be? 3.3 divided by 65536. So this is your step size in volts. If you want to understand, if you want to check your voltage in voltage or volts, you will use this, or you will use the second line if you want to check, if you want to identify your step size into millivolts. So I just did nothing but converted 3.3 volt to 3.3 millivolt conversion. Then the rest of the code is very simple. While true is our infinite loop. Reading is equal to pot.read. Pot is what? The ADC that we initialized, which is channel number 0 or GP26. Pot.read. Then MV is equal to reading into step MV and print MV. This will just print your millivolts value. However, what I'm going to do first is I will try to print the reading itself so that it gives you an idea of what exactly is that we have connected to the ADC. Now what I'm going to do is I'm going to upload this code into the PicoW board that I have, and then I'll be connecting a pot to those pins. Let me just open my camera first. I'll show you the connections that I'm doing for this experiment. So I hope the board is visible to you now. This is the pot I have, a very simple pot. You can use any kind of pot. I have connected 3 wires or soldered 3 wires to it. The end 2 should go to 3.3 and ground. Doesn't matter which one goes to 3.3 and which one goes to ground. And the middle has to go to GP26. So I'll make the connections now. The third pin from this side is my ground pin. Then just one pin below, I have 3.3 volts. And then this should go to GP26. Now GP26 is pin number 31 or ADC 0 pin. You can simply count from the bottom. This is 21, 22, 23, 24, 25, 26, 27, 28, 29, 30 and 31. That's it. The pot is connected. Let's run this code. I will keep it here. We'll keep camera here and I'll run this code. Okay, there is an error. So first of all, I will simply stop whatever is going on. Then I will have to check my pico wire once, remove and reconnect. Now you are good to go. So currently it is displaying 64223. It's close to the maximum value because the pot is at one extreme level. Okay. Now I'll move the pot a little bit towards my side or towards the ground side. At this point, I think it would be good if we can check the voltage reading. This is purely for experimentation. If you don't have a multimeter, don't feel obliged to arrange one. Just good to do, but not a must to do. I'm going to connect this to ground pin. And now I'm going to check this voltage. So I'll just keep it here. Okay. Now, if you can check, the current voltage is 2.74 or 75. Let's not disturb that pin. My Thoni again restarted. Let's not disturb that point. And what we'll do is, we will print both the digital input and the millivolt reading as well. And then I'll just give a new line so it's easier for me to identify between the two. Now if you see 2762 is the millivolt readout that I'm getting. It means 2.7 volt. Let me check it once again. (2.74), 2.75. The value we were getting was 2583. So a pot will always give some variation in the readouts. All in all, you can understand that this is how you can experiment with it. If you keep rotating it and if you go to the furthest end towards the ground pin, then you will experience the reading to be dropping completely. I'll just go down on this end of the scale. And if I keep the pot towards the other end, I will get the maximum readout. The minimum readout we are getting, it's still for 1 volt. That is probably the limitation that this pot is giving us, that it's not giving a proper 0 when given or when moved to the other end. If you use a good quality potentiometer, definitely you will get some better voltage readouts over here. However, at any point, you can remove the pot. Okay, I have removed the pot. What I'll do is pin number 21, 2, 3, 4, 5, 6, 7, 8, 9, 10, 31. Okay, this is pin number 31, and I just have a single open pin for my usage. This is the best experiment or the simplest experiment that you can do, and I'm going to connect it to 3.3 volt over here. Sorry, I am connected it to the ground pin, the third pin from top. So I'm getting the minimum reading as 256, 12 millivolt or something, and then I'm connecting it to 3.3 volt, which is giving me 3299.95 as my readout. So this is how you can experiment with an ADC. A pot is just a tool for experimentation, but the real fun lies when you actually connect some sensors with the ADC and read its values. Try this out to your end. If you have a multimeter, keep checking onto it as well. Thank you for watching this video.